In December 2025, two rare events line up in a way that scientists cannot simply ignore. An interstellar object, 3I Atlas, approaches the inner solar system at the same time the largest sunspot in over a decade, AR4294, rotates into direct view of Earth. There is no confirmed connection, but the timing is precise. The geometry is unusual, and as new tracking and solar data arrive in real time, a growing number of questions refuse to settle. In this episode, we examine what we actually know about 3I Atlas, what makes its trajectory and composition stand out, and why extreme solar activity, on the scale of a Carrington-class event, remains one of the most underestimated risks to modern civilization. If you care about evidence, uncertainty, and following the data where it leads, consider liking and subscribing. Let us begin with the facts and the coincidence that made scientists pause. On October 29, 2025, at 7:47 in the morning Eastern Time, an interstellar object passed behind the Sun. At that moment, 3I Atlas reached the closest point in its trajectory to our star, at a distance of roughly 203 million kilometers from Earth. Every telescope lost sight of it at the same time. This was not a technical failure and not a gap in coverage. It was a result of geometry. Solar conjunction occurs when the Sun moves directly between Earth and a distant object. The brightness of the solar disk and its surrounding corona overwhelms all instruments. Light scatters in every direction. Sensors saturate. For roughly 2 weeks, no optical, infrared, or spectroscopic system could observe 3I Atlas in any meaningful way. During that interval, the object was effectively invisible. This period matters because 3I Atlas is not an ordinary body. It is only the third confirmed interstellar object ever detected by human instruments. It did not form in our solar system. It entered from interstellar space, carrying information from a region far beyond the Sun's influence. Its path into our neighborhood was one among billions of possible trajectories. Yet its closest approach to the Sun occurred during the only time when Earth could not watch. The loss of visibility was complete. Any changes in motion, structure, or activity during that passage happened without direct observation. 5 weeks later, another event draws attention. A large sunspot complex rotated into view on the Earth-facing side of the Sun. It carries the designations Active Region 4294, Active Region 4296, and Active Region 4298. Together, they form one of the largest active regions observed in more than a decade. The magnetic classification is beta, gamma, delta, which represents the highest level of magnetic complexity used in solar monitoring. Regions of this type are capable of producing X-class solar flares, the most powerful category measured. The combined size of this complex is roughly 90% of the sunspot associated with the 1859 Carrington event, the strongest geomagnetic storm in recorded history. These two developments converge on the same calendar window in December 2025. One event was hidden from view. The other is visible and well monitored. The central question is not whether they are connected. At present, science does not have the tools or evidence to establish such a link. The more grounded question concerns probability. How often should two rare and unrelated events align this closely in time and geometry? To address that question, it helps to return to what is known with certainty about the hidden window. 3I Atlas was discovered on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. Within days, its motion revealed something unusual. The object was moving too fast to be gravitationally bound to the Sun. Its trajectory was hyperbolic, meaning it would pass through the solar system once and never return. This placed it in the same category as Oumuamua in 2017 and Borisov in 2019. The first two known interstellar visitors. 3I Atlas differed from both. At discovery, its speed was approximately 137,000 miles per hour. By the time it reached perihelion, the point of closest approach to the Sun, its velocity increased to roughly 153,000 miles per hour. Estimates based on its composition and motion suggest an age between 7 and 11 billion years, making it older than the Sun itself. Its trajectory carried it close to Mars, then near Venus, later past Jupiter, and finally toward Earth. On December 19th, it reaches its closest point to our planet at a distance of about 269 million kilometers. Such planetary encounters are possible for natural objects, but they are uncommon. Harvard astrophysicist Avi Loeb estimated the probability of this specific alignment occurring by chance at roughly 0.005%, or about 1 in 20,000. That number does not imply intent or design. It simply describes rarity. In science, rare events demand closer examination, not because they are extraordinary, but because they test the limits of existing models. The most important feature of the trajectory is not where the object traveled, but when. Perihelion represents a critical moment for any body passing through the inner solar system. At this point, gravitational forces are strongest and velocity is highest. For spacecraft, this is the most efficient time to perform a maneuver known as an Oberth maneuver. The Oberth effect is a basic principle of orbital mechanics. A propulsion burn performed at high speed produces a larger change in energy than the same burn performed at low speed. The deeper an object falls into a gravitational well, the more kinetic energy it can gain or redirect. Every interplanetary mission launched by humanity relies on this principle. At perihelion, the Sun delivered approximately 33 gigawatts of solar radiation to the surface of 3I Atlas. That amount of energy is comparable to 1/3 of the total nuclear power generation capacity of the United States. If the object possessed any ability to absorb, store, or use that energy, perihelion would have been the moment of maximum potential. That moment occurred during solar conjunction, when Earth-based observation was impossible. There is a straightforward counterargument. The solar conjunction was not a choice. It resulted from the relative positions of Earth, the Sun, and the object. If Earth had been on the opposite side of its orbit, the entire perihelion passage would have been observable. In this view, the timing was coincidental. This explanation is valid, but incomplete. The trajectory of 3I Atlas was fixed long before it entered the solar system. Its path was determined when it crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space. That crossing occurred roughly 8,000 years ago. If the trajectory was calculated or selected, it happened long before human civilization developed astronomy, or even writing. Intent cannot be inferred. Only outcomes can be measured. The outcome is that 3I Atlas passed through perihelion during a 2-week window of complete invisibility. Any course corrections, structural changes, or interactions with the solar environment occurred out of view. Shortly afterward, the Sunspot complex rotated into sight. Sunspots do not appear suddenly. They form through complex interactions within the Sun's magnetic field, unfolding over days and weeks beneath the solar surface, the rotation of the complex onto the Earth-facing disk, however, coincided closely with the re-emergence of 3I Atlas from behind the Sun. By late November, The complex had grown into one of the largest active regions of solar cycle 25. Correlation does not imply causation. This principle must remain central. Solar cycle 25 has exceeded earlier predictions. With activity levels not seen in more than 20 years, large sunspots are expected during solar maximum. The appearance of a major active region in late 2025 is consistent with known solar behavior. What is unusual is the timing alongside the arrival of an interstellar object. It is important to be clear about what is not being claimed. There is no claim that 3I Atlas caused the sunspot. There is no claim of artificial manipulation of solar activity. There is no claim of a coordinated threat. Such conclusions would require evidence that does not exist. The claim is narrower. The timing is uncommon. The geometry invites scrutiny. The convergence raises questions that deserve careful examination rather than dismissal. The prevailing scientific consensus is that 3I Atlas is a comet. It displays a coma, the cloud of gas and dust surrounding an active nucleus. Spectroscopic measurements have identified carbon dioxide, cyanide, and other compounds consistent with cometary material. Official statements from NASA describe behavior consistent with an active comet. This explanation may be correct. However, it does not account for every observation. 3I Atlas survived perihelion intact. In late September, it passed through a coronal mass ejection and was exposed to temperatures exceeding 5,500 degrees Celsius. Many comets fragment under far less extreme conditions. The nucleus remained whole. Observations from space-based coronagraphs detected a blue-word color shift near perihelion. Dust-scattered sunlight typically appears reddened, not bluer than the sun. The excess blue emission suggests additional processes, possibly involving gas molecules or other mechanisms. The object also exhibits an unusually high ratio of nickel to iron in its surrounding plume. These ratios exceed those commonly observed in comets and resemble compositions more often associated with processed materials. Each anomaly has plausible natural explanations. Together, they form a pattern that Avi Loeb rated as a 4 on a scale from 0 to 10, where 0 represents a clearly natural object and 10 represents a clearly artificial one. A rating of 4 does not imply alien technology. It indicates unresolved uncertainty. The data does not yet allow the question to be closed. The sunspot complex continues its rotation across the solar disk. In roughly 2 weeks, it will move to the far side of the Sun, temporarily reducing the risk of Earth-directed flares. Sunspots, however, can persist through multiple rotations. Active region 4294 may return near the end of December, facing Earth again as 3I Atlas reaches its closest approach. December 19th, 269 million kilometers. The nearest an interstellar object has ever come to Earth while modern instruments are watching. The hidden window has closed. The questions it raised remain open. What occurred behind the Sun on October 29th? What relationship, if any, exists between an ancient interstellar traveler and a major disturbance on our star? As both events converge on Earth in the final weeks of the year, the focus turns to observation. In astrophysics, the observation window refers to the limited period during which a transient event can be studied before it fades or moves beyond reach. For 3I Atlas, that window was interrupted at the most critical moment. We observed its approach, tracked its brightening, and analyzed its spectra. Then the geometry of the solar system blocked the view, leaving a gap that cannot be filled after the fact. What happened behind that curtain remains unknown. During the period of solar conjunction, several space-based observatories attempted to collect what information they could, working around the limits imposed by geometry and light. The Parker Solar Probe, operating closer to the Sun than any spacecraft before it, continued measuring the local plasma environment, magnetic fields, and energetic particles. Its instruments are not designed to image small objects, but they are sensitive to changes in the solar environment that might signal unusual interactions. The Solar and Heliospheric Observatory, positioned at the first Lagrange point between Earth and the Sun, used its coronagraphs to block the solar disk and observe the surrounding corona. These instruments can sometimes detect comets as faint streaks of light, but the glare during conjunction severely limits resolution. At the same time, the European Space Agency's JUICE mission, currently on its long journey toward Jupiter, passed within roughly 64 million kilometers of 3I Atlas on November 4th. This was not a planned encounter. JUICE was not built to study interstellar objects, but mission controllers directed its instruments toward the visitor as an opportunity observation. The data gathered from Parker, from SOHO, and from JUICE is still being processed. Interpreting it will take months. The signals are indirect, fragmented, and difficult to separate from background solar noise. While analysis continues, the object itself moves steadily outward, growing fainter as it recedes from the Sun and from Earth. The Sun, however, remains fully visible. Active region 4294 sits on the solar disk as an unresolved problem. Its magnetic field lines are twisted into configurations that store enormous amounts of energy. These fields are not static, they shift, shear, and evolve as plasma flows beneath the solar surface. At any moment, stressed magnetic lines can reconnect, releasing energy suddenly. When this happens, the result is a solar flare, often accompanied by a coronal mass ejection. Forecast models indicate that the probability of X-class flares from this region remains elevated. The probability of a flare approaching Carrington-class intensity is low, but it is not zero. This matters because modern civilization depends on electromagnetic stability, electrical power grids, communication networks, satellite constellations, navigation systems, financial infrastructure, transportation control, and data centers all rely on controlled flows of electrons through copper and silicon. A sufficiently strong solar storm can disrupt those flows. Induced currents appear where they are not expected. Systems behave in ways their designers never intended. This is not speculation. It reflects decades of research by engineers and physicists who study space weather and its effects on technological systems. The open question has never been whether a severe solar storm can happen again. It has always been when. That is the context in which December 2025 arrives. A historically large sunspot complex faces Earth. At the same time, an interstellar object of uncertain properties approaches its closest pass. The hidden window has closed. In its place is a window of convergence. What can be learned from it depends on careful observation and restraint. To understand the risk, it helps to understand the nature of sunspots themselves. The Sun has always marked its surface. Long before any observer existed, dark regions formed and faded on the photosphere. We call them sunspots, though the name minimizes their nature. They are not surface blemishes. They are regions where intense magnetic pressure disrupts the normal flow of energy from the Sun's interior. These regions are cooler than their surroundings, which is why they appear dark by contrast. Cooler, in this context, still means temperatures of roughly 4,000 degrees Celsius, hot enough to vaporize any known material. Sunspots form through the solar dynamo, a process driven by the motion of electrically charged plasma beneath the sun's surface. The sun does not rotate as a solid body. Near the equator, it completes a rotation in about 25 days. Near the poles, rotation is slower. This differential motion stretches and twists magnetic field lines over time. As these fields become more tangled and stressed, they can break through the surface, creating sunspots. Not all sunspots are equally dangerous. Size alone does not determine risk. The key factor is magnetic complexity. Simple sunspots have a bipolar structure, with one magnetic polarity on one side and the opposite polarity on the other. These are classified as beta regions. They can produce flares, but typically of limited strength. More complex regions develop additional polarities. In beta-gamma regions, magnetic field lines from different sources interact in tangled patterns, increasing stored energy. The most dangerous configuration is beta-gamma delta. In this case, opposite magnetic polarities exist within the same sunspot umbra. This creates extreme magnetic stress. Active region 4294 carries this classification. The energy stored in such a configuration is vast. When magnetic field lines of opposite polarity are forced close together, they can suddenly reconnect. This process, called magnetic reconnection, releases energy explosively. During reconnection, particles are accelerated to near the speed of light. Plasma is heated to tens of millions of degrees. Radiation is emitted across the electromagnetic spectrum, from radio waves to gamma rays. This is a solar flare. Flares are classified on a logarithmic scale. Class flares are common and usually cause minor effects. M-class flares are stronger and can disrupt radio communications and satellites. X-class flares are the most powerful. Within that category, the scale continues upward. An X-zone flare is significant. An extend flare is severe. The Carrington event of 1859 is estimated to have involved a flare between X40 and X50. In the first week of December 2025, the sunspot complex that includes active region 4294 produced multiple class flares and several M-class events. On December 1st, a nearby region, active region 4299, rotated back into view and produced an X-zone 0.9 flare. This was the same region responsible for major activity earlier in the month, including an X5.16 flare, the strongest observed that year. The sun has not been calm. The largest sunspot complex of the current solar cycle now faces Earth. The flare itself is only the first stage of a severe space weather event. Electromagnetic radiation from a flare travels at the speed of light, about 8 minutes after reconnection occurs on the sun. X-rays and ultraviolet radiation reach Earth. These emissions can ionize the upper atmosphere, disrupting high-frequency radio communications on the daylit side of the planet. Polar aviation routes can lose reliable contact. Navigation signals can degrade. More dangerous are coronal mass ejections. These are massive clouds of magnetized plasma launched from the sun, often following major flares. A coronal mass ejection can contain billions of tons of material and travel at speeds exceeding 2,000 kilometers per second. Unlike radiation, these are physical structures. They take time to reach Earth, usually between 15 hours and several days. When a coronal mass ejection strikes Earth's magnetosphere, the effects can be severe. The magnetosphere, generated by motion in Earth's molten iron core, normally deflects most charged particles from the sun. A strong impact can compress and distort this shield. Charged particles are guided toward the poles, producing auroras. During ordinary conditions, Auroras are visible only at high latitudes, above roughly 60 degrees north or south. During extreme storms, they appear far closer to the equator. During the Carrington event, auroras were seen in Cuba, Hawaii, and near the equator in South America, where the night sky became bright enough to read by. The visual display hides the danger. As charged particles move through Earth's magnetic field, they induce electrical currents in long conductors. Power lines act like antennas. Pipelines develop voltage gradients. Rail systems carry unexpected charges. Transformers, which regulate voltage across the power grid, can be driven into saturation. Once damaged, large transformers are difficult to replace. Manufacturing and installing them can take months. History provides warnings. In March 1989, a geomagnetic storm caused the collapse of the Hydro-Quebec power grid. 6 million people lost electricity for 9 hours. That storm was roughly 3 times weaker than the Carrington event. In July 2012, a Carrington-class storm erupted from the Sun and crossed Earth's orbital path. Earth missed it by about 9 days. The margin was narrow. Modern infrastructure was spared by chance alone. Active Region 4294 has the magnetic complexity and stored energy needed to produce a comparable event. This assessment comes from space weather forecasters at the National Oceanic and Atmospheric Administration, at the European Space Agency, and at observatories worldwide. Whether that energy will be released while the region faces Earth cannot be predicted in advance. Whether a resulting coronal mass ejection would be directed toward our planet is also uncertain. These variables depend on conditions that cannot be measured until after the fact. Against this backdrop, the timing stands out. The Sunspot complex rotated into view as 3I Atlas emerged from behind the Sun. This is a statement of chronology, not causation. Large sunspots appear regularly during periods of high solar activity. Solar cycle 25 has been more active than expected, with sunspot counts exceeding forecasts. The emergence of a major active region in late 2025 fits within known solar behavior. At the same time, the Sun is a dynamic system of immense complexity. The broad principles of the solar dynamo are understood, but the details are not. Scientists cannot predict exactly when sunspots will form, how large they will grow, or which magnetic configurations will produce major flares. The physics is known. The system is too complex for precise forecasting. This leads to a cautious question. Could an external influence affect solar activity? At first glance, the idea seems implausible. The Sun contains nearly all the mass in the solar system. Its internal energies dwarf anything humans have ever produced. A small object, even an interstellar one, would appear insignificant by comparison. Yet during perihelion, 3I Atlas passed through regions of intense solar magnetic field. The object itself may carry magnetic properties, either inherited from its formation or induced by interaction with the solar wind. At the velocities involved, any interaction between the object's magnetic environment and the Sun's complex field would have been brief, but potentially measurable. There is no data from the perihelion passage to test this directly. The hidden window prevented observation. What is known is what followed. A sunspot complex of historic size rotated into Earth view. A magnetic configuration capable of producing severe space weather is now in place. An interstellar object of uncertain nature continues its passage. The timing is precise enough to demand attention, even if it ultimately proves coincidental. The Sun has wounded itself many times before, and it will do so again. The question that hangs over December 2025 is not whether the Sun is capable of producing another major disturbance, but but whether the particular wound now facing Earth is simply coincidence, or whether its timing carries deeper significance. The Sun continues to rotate, steady and indifferent. Each day, the sunspot complex drifts closer to the western limb of the solar disk. With that movement, the angle at which any flare or eruption could strike Earth slowly decreases. In roughly 2 weeks, active region 4294 will rotate out of view, slipping to the far side of the Sun where any outbursts cannot directly affect our planet. That would normally mark a reduction in immediate risk. But sunspots do not necessarily vanish when they rotate out of sight. The dark regions we observe are only surface expressions of much larger magnetic structures beneath the photosphere. Those structures can persist even when the visible sunspot fades. If the underlying magnetic fields remain coherent, the sunspot can survive the journey around the far side of the Sun and return into view roughly 1 solar rotation later. Active region 4294 belongs to a broader active complex that has been producing sunspots for weeks. Measurements suggest continued magnetic flux emerging from the convection zone below. This increases the likelihood that the region will persist. If it does persist, the timing becomes notable. December 19th marks the closest approach of 3I Atlas to Earth. At a distance of approximately 269 million kilometers, around December 25th, give or take a day or two, active region 4294 could rotate back onto the Earth-facing disk. The interval between these dates represents a narrow window in which 2 rare conditions overlap: an interstellar object passing at its nearest point, and a potentially historic sunspot once again aimed toward Earth. A solar flare during this window would reach Earth in roughly 8 minutes, the time it takes light to travel from the Sun to our planet. A coronal mass ejection would follow later, typically between 15 and 36 hours after eruption. Depending on its speed, none of this proves a connection. The Sun does not track comets. 3I Atlas has no known mechanism to influence solar magnetic fields. Under known physics, the timing is remarkable but presumed meaningless. And yet the convergence focuses attention. Abstract risks become concrete when conditions align. Space weather ceases to be a background concern when a large, complex sunspot faces Earth. Interstellar objects become more than academic curiosities when one passes so close. Observation and preparation are the only responses available. The Sun cannot be controlled. The object cannot be redirected. The only question is whether the wound closes quietly or opens again. To understand why this matters, it helps to return to history. On the morning of September 1st, 1859, the English astronomer Richard Carrington was doing what he did almost every clear day from his private observatory in Redhill, south of London. He was carefully sketching sunspots projected onto a screen. Carrington was known for precision. He had already demonstrated that the Sun rotates faster at its equator than at its poles, a key insight into solar behavior. That morning, while observing a large sunspot group, he saw something entirely new. A sudden flash of intense white light erupted from the region. It lasted for only about 5 minutes, but it was bright enough to be visible against the brilliant surface of the Sun itself. Carrington immediately understood that the event was unusual. He attempted to find a witness, but by the time he returned, the light had faded. Unknown to him at the time, another astronomer, Richard Hodgson, had observed the same flash independently. Their combined reports later confirmed that the event was real and solar in origin. Carrington suspected a connection between the flash and disturbances on Earth, but he remained cautious. He famously wrote that one swallow does not make a summer, emphasizing the need for evidence before claiming causation. The evidence arrived the following day, on September 2nd, 1859. Earth was struck by the most intense geomagnetic storm ever recorded. Telegraph systems across Europe and North America failed almost simultaneously. Operators reported electrical shocks. Telegraph paper caught fire. Sparks jumped from pylons. In one of the most striking details, some operators discovered they could continue sending messages even after disconnecting their power supplies. The induced currents from the storm were sufficient to run the equipment. The aurora that night was visible around the world. In the Rocky Mountains, miners woke and prepared breakfast, convinced that dawn had come early. In the northeastern United States, people read newspapers by the light of the sky. In the Caribbean and in Hawaii, places far from the poles, the night glowed red and green. The storm persisted for days. When it ended, systems were repaired and life resumed. The event entered scientific history as a curiosity and a demonstration of solar power. Civilization in 1859 was largely unaffected because it did not depend on complex electrical systems. Telegraph lines were damaged, but there was little else to lose. The storm was dramatic, but not catastrophic. 166 years later, the situation is entirely different. Modern civilization is built on electromagnetic infrastructure. Electricity flows through high-voltage transmission lines spanning thousands of kilometers. Communications depend on satellites, fiber optic cables, wireless networks, and data centers. Financial systems process transactions at electronic speeds. Transportation systems rely on satellite navigation. Medical care depends on powered equipment. The systems that support daily life are tightly interconnected and sensitive to electrical disturbance. If a Carrington-class geomagnetic storm were to strike Earth today, the sequence of events is well understood. The first warning would come from spacecraft positioned near the first Lagrange point, about 1.5 million kilometers sunward from Earth. Satellites, such as the Deep Space Climate Observatory, continuously monitor the solar wind. When a fast coronal mass ejection approaches, these instruments detect changes in particle density and magnetic field orientation. The warning time depends on speed. For the fastest events, it may be as little as 15 minutes. For slower ones, perhaps an hour. This is not enough time to protect infrastructure on a large scale. When the coronal mass ejection reaches Earth, it strikes the magnetosphere like a wave hitting a barrier. The magnetic field compresses on the sunward side and stretches on the night side. Magnetic reconnection occurs, transferring energy into the upper atmosphere. Geomagnetically induced currents begin to flow. These are not controlled currents. They arise when a changing magnetic field interacts with long conductors on Earth's surface. Power transmission lines become antennas. The longer the line, the greater the induced voltage. Transcontinental lines are especially vulnerable. Transformers are the critical weak point. Power is transmitted at high voltage to reduce losses. Transformers step voltage up at generation and step it down near consumers. These devices are massive, expensive, and custom-built. There is no large reserve of spare transformers. Geomagnetically induced currents can saturate transformer cores, causing rapid overheating. Windings can melt. Insulating oil can ignite. When one transformer fails, its load shifts to others, which may then fail in sequence. This cascade was demonstrated on a small scale during the March 1989 geomagnetic storm that collapsed the Hydro-Quebec power grid in 90 seconds. That storm was roughly 3 times weaker than the Carrington event. 5 million people lost power for 9 hours. Transformers were damaged as far south as New Jersey. A Carrington-class storm would be far more severe. Studies commissioned by the United States government and by international insurers have attempted to quantify the impact. Estimates suggest direct damage to electrical infrastructure in the United States alone could exceed $600 billion. Total economic losses, including cascading effects, could reach $2.6 trillion. Power outages in some regions could last months or longer. Large transformers take time to manufacture and install. Without electricity, fuel pumps fail. Without fuel, transportation stops. Without transportation, supply chains collapse. Hospitals rely on backup generators. But those generators require fuel deliveries that may not arrive. Water treatment plants shut down. Sewage systems fail. Food spoils. Communications networks go offline. Modern cities are not designed for prolonged power loss. Population density, which makes urban life efficient, becomes a liability when logistics fail. A typical supermarket holds only a few days' worth of food for the surrounding population. Warehouses contain more. But without powered transportation and coordination systems, supplies cannot move. Cellular networks fail as backup batteries drain. Internet access disappears as data centers overheat. Emergency coordination becomes difficult just when it is most needed. This assessment is not speculative. It is shared by engineers, physicists, and policy experts who study infrastructure resilience. The United States Federal Energy Regulatory Commission has acknowledged the risk. The Royal Academy of Engineering in the United Kingdom has issued similar warnings. The insurance industry has modeled potential losses. Across disciplines, the conclusion is consistent. Modern civilization is vulnerable. Preparation is limited. The sun is indifferent. The probability of a Carrington-class event in any given year is low. Estimates vary, ranging from roughly 1% to 12% per decade depending on the statistical model. Over a single year, the risk appears small. Over the lifetime of modern electrical infrastructure, the cumulative probability becomes significant. The question shifts from whether such an event will occur to when. In this context, the present moment stands out. A large, magnetically complex sunspot faces Earth. An interstellar object passes near our planet. The alignment may be coincidence. Most likely, it is. But the convergence sharpens attention. It reminds us that rare events do occur, that history offers warnings, and that the systems we depend on are not as resilient as we might assume. Some preparations are possible. Monitoring can improve. Infrastructure can be hardened. These measures matter, but they cannot eliminate risk. The sun will continue to wound itself, and someday, one of those wounds will matter again. Utilities do have options to reduce damage from severe space weather. Sensors can be installed to detect geomagnetically induced currents and automatically trip circuits before transformers overheat. Grid operators can lower electrical loads during storm warnings, reducing stress on vulnerable components. Governments can stockpile certain critical transformer parts, though doing so is expensive and logistically complex. None of these measures is simple. All require long planning timelines, sustained funding, coordination across agencies, and political commitment. They also require accepting a risk that feels abstract until the moment it becomes immediate. That acceptance has always been difficult. This is where December 2025 finds us. A sunspot complex capable of producing the flares that drive geomagnetic storms faces Earth. Active region 4294 carries the beta, gamma, delta magnetic classification, indicating stored energy sufficient for major events. Whether that energy will be released while the region is oriented toward our planet remains unknown. The Carrington event occurred near the peak of solar cycle 10. We are now near the peak of solar cycle 25. The parallel is not exact, but it is close enough to warrant attention. Richard Carrington observed the sun out of curiosity. He recorded what he saw because he believed careful, systematic observation had value even when the significance was not immediately clear. He could not have known that his sketches and notes would become the reference point against which future solar storms would be measured. We watch the sun now for different reasons. We watch because modern civilization depends on uninterrupted electrical and electronic systems. The terms of the equation have changed. Observation is no longer only about understanding nature. It is about managing risk. There is another dimension to that risk which extends beyond the immediate threat of a single storm. The Carrington event was not unique in Earth's history. Evidence preserved in Antarctic ice cores and in tree rings around the world shows that far more powerful solar events have occurred. One of the most studied is the Miyake event of the year 774. That event produced a sharp spike in carbon-14 levels, indicating an intense burst of high-energy radiation. Estimates suggest it may have been roughly 20 times more powerful than the Carrington event. Similar spikes appear at other points in the geological record. These ancient events occurred long before the development of electrical technology. They left chemical signatures in ice and wood but caused no technological damage because there was no technology to damage. The sun has not become more active over long timescales. The frequency of extreme events appears to have remained relatively stable for billions of years. What has changed is vulnerability. Each new satellite placed in orbit, each new transmission line constructed, each new data center brought online adds to the systems exposed to space weather. The pace of this expansion is accelerating. Transportation is becoming more electrified. Financial systems are increasingly digital. The space economy is growing. Connectivity is deepening. Exposure grows with every step. Investment in space weather monitoring and infrastructure protection has not kept pace. The warnings are clear. The probabilities are known. The potential consequences have been studied in detail. Still, preparation lags behind risk. This may reflect a basic human tendency. Rare, impersonal threats are difficult to prioritize. The sun will not announce its intentions. When a storm arrives, it will do so according to physics alone. December 2025 places us in a familiar position. Watching, waiting. The sunspot continues its slow rotation. The interstellar visitor continues its approach. The convergence unfolds under laws we understand but cannot influence. The Carrington equation remains unchanged. Vulnerability multiplied by impact multiplied by probability defines risk. Over the past century, vulnerability and impact have increased steadily. Probability belongs to the sun. Understanding why 3I Atlas continues to draw attention requires a shift in focus. Science advances by comparing expectation to observation. When observations match predictions, they confirm existing models. When observations deviate, they invite scrutiny. One deviation may be noise. Several deviations, clustered around the same object, demand closer examination. Since its discovery in July, 3I Atlas has accumulated 9 documented anomalies. Each one, considered alone, has a plausible natural explanation. Interstellar objects are diverse. They form in environments we cannot directly study. Unexpected behavior is not the same as impossible behavior. But 9 anomalies represent a pattern that cannot be ignored. The first anomaly is the trajectory alignment. An interstellar object can enter the solar system from any direction. Space surrounds us in 3 dimensions. Over many detections, arrivals should be distributed roughly randomly across the sky. 3I Atlas entered on a path within 5 degrees of the ecliptic plane, the flat disk defined by Earth's orbit and shared by the planets. For a random interstellar object to align this closely is statistically unusual. The probability is estimated at roughly 0.2%, or about 1 in 500. This is not impossible. It is simply the first deviation from expectation. The second anomaly concerns planetary encounters. The path of 3I Atlas brought it within tens of millions of kilometers of Mars, then close to Venus, and later past Jupiter. When combined with the ecliptic alignment, these encounters form a trajectory that samples much of the inner solar system. Avi Loeb estimated the combined probability of such a path occurring by chance at roughly 0.005%, or 1 in 20,000. Other astronomers have criticized the method, arguing it may overstate the rarity. Even critics agree, however, that the trajectory is unusual. The third anomaly is timing. 3I Atlas reached perihelion, its closest approach to the Sun, during solar conjunction, when it was positioned directly behind the Sun from Earth's perspective. This geometry prevented direct observation during the most dynamic phase of its passage. The hidden window lasted roughly 2 weeks and coincided with maximum gravitational influence and maximum solar heating. A natural object does not choose its path. The conjunction followed from orbital mechanics and Earth's position. Yet if one were attempting to minimize observation during a critical phase, this is precisely the geometry that would result. The fourth anomaly is the presence of an anti-tail. Comets normally display tails that point away from the Sun. Dust tails curve gently along the orbit. Ion tails form straight lines pushed by the solar wind. 3I Atlas displayed a structure pointing toward the Sun. Antitails can occur naturally due to viewing geometry when Earth passes through a comet's orbital plane. This can create the appearance of forward-pointing material. Some observers argue that the geometry does not fully account for what was seen in this case. One interpretation suggests material being ejected forward. This remains debated. The fifth anomaly is mass. Estimates based on outgassing rates and gravitational effects suggest a mass exceeding 33 billion tons. This is far larger than typical comets and roughly 1 million times greater than estimates for Oumuamua. Mass affects how an object responds to forces such as outgassing, solar radiation pressure, and the solar wind. A more massive object follows a more stable, predictable trajectory. If these estimates are correct, 3I Atlas behaves less like a fragile icy body and more like a compact, resilient one. The sixth anomaly involves chemical composition. Spectroscopic studies of the surrounding gas reveal an unusually high ratio of nickel to iron. In most comets, these metals appear in proportions similar to those of the Sun, reflecting primordial material. In 3I Atlas, nickel dominates. Such ratios are more commonly associated with processed materials than with natural ices. One possible explanation is formation in a region with different elemental abundances. Artificial interpretations have been proposed but remain speculative. The seventh anomaly is water content. Typical comets contain substantial water ice, which drives much of their activity. 3I Atlas appears to contain only about 4% water by mass. This is far lower than expected. An object that spent billions of years in interstellar space would normally preserve volatiles rather than lose them. This suggests either an unusual formation environment or an atypical evolutionary history. The eighth anomaly is polarization. Light reflected from cometary dust becomes polarized in characteristic ways. The degree and direction of polarization reveal information about particle size and structure. 3I Atlas shows extreme negative polarization not observed in other comets. including Borisov. The signal implies dust properties unlike any previously measured in cometary environments. The ninth anomaly appeared near perihelion. Space-based observatories detected a color shift. The object appeared bluer than the Sun. This contradicts expectations. Dust scattering normally reddens reflected light. A cold surface should appear redder, not bluer. The observation suggests either an unusual emission mechanism or a source of energy hotter than the solar photosphere. Neither fits comfortably within standard comet models. 9 anomalies do not equal proof. Avi Loeb proposed a scale from 0 to 10 for assessing interstellar objects. 0 represents a clearly natural object. 10 represents a clearly artificial one. Based on current evidence, he places 3I Atlas at 4. This is not a claim of alien technology. It is a measure of uncertainty. Natural explanations remain more likely. But the margin is not overwhelming. Critics have responded appropriately. They point out that each anomaly has a plausible natural explanation. Alignment can be coincidence. Composition can reflect different stellar environments. Color shifts can arise from unfamiliar gas emissions. Extraordinary claims require extraordinary evidence. The case for artificial origin is circumstantial. This skepticism is valid. The scientific method demands it. What skepticism does not do is erase the anomalies. Alternative explanations are not confirmations. The data remains incomplete. The hidden window at perihelion removed the opportunity for decisive observation. What remains is ambiguity. That ambiguity is the reason the questions persist. And now we arrive at the question that hangs quietly over everything described so far. What are the odds? 9 anomalies. Each one individually explainable within existing physics. Cluster around a single object. That object arrives during the peak of solar maximum, when the Sun is at its most active and most unpredictable. Its closest approach to the Sun occurs during a 2-week interval when Earth cannot observe it. A massive sunspot complex rotates into view as the object emerges from behind the Sun, and the object's closest approach to Earth aligns closely with the possible return of that same sunspot to an Earth-facing position. Each element, taken alone, can be explained. The trajectory is unusual but possible. The composition is strange but not impossible. The timing is striking but could be coincidence. Large sunspots are expected during solar maximum. The difficulty lies not in any single fact, but in all of them appearing together. This is not a question that statistics can answer cleanly. Statistical methods rely on well-defined probability spaces and large samples drawn from known distributions. Interstellar objects do not meet those criteria. In the entire history of modern astronomy, only 3 confirmed interstellar visitors have been observed. With so few data points, it is impossible to calculate meaningful probabilities for unusual trajectories or behaviors. There is no baseline distribution to compare against. What science can do, in such cases, is recognize patterns. It can note when multiple deviations from expectation cluster in time and circumstance. It can acknowledge that a convergence is striking without claiming it is meaningful. The simplest explanation remains that 3I Atlas is a natural object from an unfamiliar environment, following an uncommon but physically allowed path through the solar system. This explanation fits the available evidence and requires the fewest assumptions. It is where the weight of evidence currently points. But simplicity does not erase uncertainty. The question persists in the space between observation and explanation, in the silence created by missing data. That silence invites another question. What if we are framing the problem incorrectly? To explore that possibility, it is necessary to revisit a well-established principle of orbital mechanics known as the Oberth effect. In 1929, A Romanian physicist named Herman Oberth published a book titled Ways to Spaceflight. Within it, he described a principle that initially seems counterintuitive. A rocket engine produces a greater change in energy when it fires at high speed than when it fires at low speed, even if the same amount of fuel is used. At first glance, this appears to violate common sense. Fuel is fuel. Thrust is thrust. How can speed change efficiency? The answer lies in the relationship between kinetic energy and velocity. Kinetic energy increases with the square of velocity. Doubling speed does not double energy. It quadruples it. Because of this nonlinear relationship, adding a small amount of velocity to an already fast-moving object increases its total energy far more than adding the same amount of velocity to a slow-moving one. A rocket engine works by expelling mass at high speed. The energy transferred to the spacecraft depends on how that expelled mass compares energetically to the spacecraft's motion. When a spacecraft is already moving quickly, more of the fuel's chemical energy ends up as kinetic energy of the spacecraft itself. This is the Oberth effect. In practical terms, it means that the most efficient time to apply propulsion is when an object is moving fastest. In a gravitational system that occurs near the bottom of a gravitational well, the closer an object falls toward a massive body, the faster it travels. The faster it travels, the more effective any propulsion becomes. Every interplanetary mission humanity has flown relies on this principle. Gravity assist maneuvers around planets exploit it. When Voyager passed Jupiter, it used the planet's gravity to increase its speed toward the outer solar system. When the Parker Solar Probe dives close to the Sun, it uses solar gravity to reshape its orbit. The gravitational field provides energy, and the Oberth effect maximizes how efficiently that energy can be used. Now consider 3I Atlas at perihelion. On October 29th, the object reached its closest approach to the Sun, at a distance of roughly 203 million kilometers. At that moment, it was traveling faster than at any other point in its journey through the solar system, exceeding 150,000 miles per hour. Solar gravity was strongest, velocity was highest. From the standpoint of orbital mechanics, the conditions for exploiting the Oberth effect were optimal. If 3I Atlas is a natural comet, then perihelion was simply the turning point of a hyperbolic orbit. The object fell toward the Sun, accelerated, curved around it, and departed without gaining net energy. Physics unfolded as expected, indifferent to observers. But if the object is something else, perihelion represented an opportunity. The energy environment at perihelion was extreme. At that distance, solar radiation delivers on the order of hundreds of watts per square meter to any surface facing the Sun. For an object several kilometers across, the total incoming power would be measured in gigawatts. This is comparable to the output of large nuclear power plants, delivered continuously and without fuel. That energy exists regardless of whether it is used. The question is whether anything could make use of it. If an object possessed any means of harvesting energy, perihelion would be the moment to do so. Solar panels, thermal collectors, or more advanced energy capture systems could, in principle, collect a portion of that flux. Stored energy could then be used later for propulsion, for powering instruments, or for other functions. If the object carried any propulsion system at all, perihelion would be the most efficient moment to use it. A small change in velocity at that point would produce a much larger change in the object's final trajectory than the same maneuver performed elsewhere. That is the Oberth effect in action. Perihelion also offers other advantages. Solar heating is intense. providing thermal energy for any process that requires heat. Gravitational forces are at their maximum, which can aid separation dynamics if parts of an object were to detach. Most importantly, perihelion coincided with solar conjunction. For roughly 2 weeks, 3I Atlas was unobservable from Earth. The sun's glare overwhelmed our instruments. Telescopes could not see through it. During this interval, Earth-based observation was effectively blind. This hidden window is central to the uncertainty. Anything that occurred during that period happened without direct observation. That does not mean something did happen. It means we cannot rule it out based on observation alone. Avi Loeb has suggested one possible scenario to illustrate the significance of this gap. In what he describes as a mothership hypothesis, the main body of 3I Atlas would continue on its visible, trackable trajectory, while smaller objects released near perihelion could follow different paths. These hypothetical secondary objects could use gravity to redirect toward other destinations within the solar system. The physics behind such a scenario is not speculative. Gravitational slingshot maneuvers are standard practice in spaceflight. Small objects released at high velocity near perihelion could, in principle, diverge onto new trajectories. The mathematics of such maneuvers has been understood for decades. The question is not whether it is physically possible, but whether it occurred. This is where the hidden window becomes important. Near perihelion, tidal forces and thermal stress could provide natural explanations for fragmentation. Comets sometimes break apart under intense solar heating. Fragments separate from the nucleus and follow slightly different paths. If an object released components during this period, they might initially resemble natural debris. Over time, however, differences would emerge. Objects following purely gravitational trajectories would diverge predictably. Objects undergoing propulsion would deviate. By December, careful tracking should reveal such differences. This is precisely what astronomers are now watching for. Since observations resumed in November, an international campaign has been monitoring 3I Atlas. The effort is not limited to tracking the main nucleus. It includes searches for associated fragments, unexplained companions, or deviations from expected motion. Space-based observatories such as the Hubble Space Telescope and the James Webb Space Telescope, along with large ground-based facilities, are contributing data. So far, no confirmed secondary objects have been detected. The nucleus appears intact. Its trajectory remains consistent with gravitational motion, showing no evidence of propulsion. These observations favor the natural explanation, but the campaign is ongoing. Data continues to arrive. The question of what happened during the hidden window remains unresolved because it cannot be resolved directly. The opportunity to observe perihelion has passed. It is important to state clearly what is not being claimed. There is no assertion that 3I Atlas performed an Oberth maneuver. There is no claim that it released probes or artificial objects. There is no announcement of extraterrestrial technology. What exists is a gap in observation coinciding with a moment when physics would favor any propulsive or energetic action. If such action were possible, the Oberth effect describes an opportunity, not an accusation. If 3I Atlas is a natural comet, then the hidden window is simply an inconvenience. The most dramatic phase of its journey went unseen. But nothing unusual occurred. If it is something else, then the hidden window represents a period when action could have taken place without detection. At present, the evidence favors the natural interpretation. Occam's razor applies. Simpler explanations should be preferred until evidence demands otherwise, but the hidden window prevents the question from being closed definitively. Science cannot prove that nothing happened during a period when observation was impossible. It can only examine what came afterward. That examination continues. The behavior of the object as it approaches Earth will provide further data. A purely gravitational trajectory supports the comet hypothesis. Any unexplained acceleration or deceleration would require new explanations. The presence or absence of secondary objects matters. Expected fragmentation would support natural processes. Unexpected companions would raise new questions. For now, the situation remains unchanged. Perihelion has passed. The hidden window is closed. The implications of those 2 weeks continue to echo as 3I Atlas moves toward its closest approach to Earth. What happened near the Sun may never be known with certainty, but the question itself remains worth asking. Because the answer, whatever it may be, would matter. The physics of stellar flybys has been studied for decades, though almost always in the context of spacecraft launched by humanity rather than objects arriving from interstellar space. Every deep space mission relies on gravity to shape its path. Voyager used Jupiter's gravity to accelerate toward the outer planets. Cassini passed Venus, Earth, and Jupiter before reaching Saturn. New Horizons used Jupiter to shorten its journey to Pluto. In all of these cases, the underlying mechanics are well understood and well tested. When a spacecraft approaches a massive body, it accelerates as it falls into the gravitational well. If it passes behind that body relative to the body's motion through space, it can gain a small amount of orbital momentum and leave faster than it arrived. If it passes in front, it can lose momentum and slow down. This exchange is called a gravity assist. For 3I Atlas, the Sun played the role of the massive body. Its trajectory carried it around the back of the Sun relative to the Sun's motion through the galaxy. That geometry would provide a slight increase in velocity, though for an object already traveling at interstellar speeds, the effect is small. The Oberth effect operates on a different principle. It does not depend on stealing momentum from a planet or star. It depends on speed. Any propulsion applied when an object is moving very fast is more efficient than the same propulsion applied when it is moving slowly. This remains true regardless of geometry. At perihelion, 3I Atlas was moving at its maximum velocity. Any propulsive action at that moment would have had the greatest possible impact on its final trajectory. To understand how sensitive such moments are, consider a very small change in speed, a velocity change of 1 meter per second. Roughly the speed of a slow walk would be enough to alter the object's predicted position by a measurable amount over the following months. Modern astrometry is precise enough to detect such deviations. This is not hypothetical. When Oumuamua passed through the solar system, astronomers detected a non-gravitational acceleration on the order of 1 millimeter per second squared near perihelion. The cause of that acceleration remains debated. Outgassing of invisible volatiles is the leading natural explanation, but it has not been conclusively demonstrated. If 3I Atlas were to show a similar deviation, the same discussion would likely follow. A larger change in velocity would have even more dramatic consequences. At interstellar speeds, small changes in direction translate into enormous differences over time. An object that enters the solar system on one path could leave on a very different heading if propulsion were applied at the right moment. Such a change would eventually be detected as the object moves against the background stars. The mathematics of orbital motion is exact. Deviations cannot hide indefinitely. But by the time they are detected, any maneuver would already be complete. This is where the hidden window becomes relevant again. Any propulsive action that occurred during solar conjunction would have taken place without direct observation. This may mean nothing. It may simply reflect the geometry of Earth's orbit and the timing of the object's passage. or it may reflect something else. The question is not whether the Oberth effect is real. It is a fundamental principle of physics that we use routinely. The question is whether an interstellar visitor made use of that principle during the 2 weeks when no telescope on Earth could see it. At this point, discussion often shifts away from physics and toward broader frameworks for thinking about extraterrestrial intelligence. One of the most widely discussed is the idea known as the dark forest. The concept traces back to a question posed in 1950 by physicist Enrico Fermi. Given the age and size of the galaxy and the number of stars with potentially habitable planets, why do we see no evidence of other civilizations? This question became known as the Fermi paradox. Many explanations have been proposed. Life may be rare. Intelligence may be fragile. Civilizations may destroy themselves before spreading beyond their home systems. Interstellar travel may be impractical. In 2008, Chinese author Liu Cixin introduced a different possibility in his novel, The Dark Forest. He suggested that the universe might be fundamentally hostile. In this view, every civilization seeks survival. Resources are finite. Communication across interstellar distances is slow and unreliable. Intentions cannot be verified. Under these conditions, revealing one's existence becomes dangerous. In the dark forest framework, the rational strategy is silence. Any civilization that reveals itself risks being targeted by others that fear competition or future threat. A civilization that detects another faces a dilemma. If it waits, the other may grow stronger. If it communicates, it reveals information. The safest course, under this logic, is to remain hidden or to eliminate potential rivals before they can act. The result is a galaxy that appears empty, not because it lacks life, but because those who survive do so quietly. This idea is provocative and deeply controversial. It assumes a level of universal risk aversion that may not exist. It treats all civilizations as rational actors with similar priorities. It ignores the potential benefits of cooperation. Most importantly, it is not a testable scientific theory. It makes predictions that cannot be verified or falsified with current observations. For these reasons, it does not belong to mainstream astrophysics. But relevance does not require correctness. The dark forest hypothesis matters because it challenges assumptions. It asks what kinds of behavior might be invisible to us. It reminds us that absence of evidence is not evidence of absence. As a conceptual stress test, it raises uncomfortable questions about how advanced civilizations might behave if they exist. Viewed through that lens, it becomes possible to ask what a reconnaissance probe might look like if a civilization wished to observe other systems without drawing attention. It would not broadcast signals. It would not follow obviously artificial trajectories. It would resemble something common and expected. Comets fit that description well. Every star system produces icy remnants during planet formation. Many are scattered into interstellar space. An interstellar comet would not be surprising. It would attract scientific interest, but not immediate alarm. Such an object would follow gravitationally plausible paths. As it approached a star, it would heat up and produce a coma and tail. It would behave like a comet because it would need to look like one. Any internal systems could be masked by natural outgassing. Heat signatures could be obscured. Instruments could operate quietly beneath a layer of dust and gas. This line of thought leads naturally back to 3I Atlas. The object exhibits cometary behavior. It follows a physically allowed trajectory. It does what comets do. At the same time, it shows anomalies that keep questions open. The dark forest framework suggests one possible way to interpret such ambiguity, not as evidence, but as a reminder of how difficult detection might be. The idea can be taken further, but doing so quickly leaves the domain of science and enters speculation. Some have suggested that an advanced civilization might prefer indirect methods of influencing a target system. Direct attack reveals intent and location, but if natural processes can be leveraged, the outcome might appear accidental. Solar activity is a powerful force. A sufficiently strong coronal mass ejection can strip atmospheres or disrupt technological civilizations. Even a storm on the scale of the Carrington event could collapse infrastructure without leaving clear evidence of external interference. Is it possible to trigger such an event artificially? There is no evidence that it is. Our understanding of solar physics is incomplete, but we do not know how to control or initiate solar flares. The Sun is a chaotic system with dynamics that remain difficult to predict even with modern models. Ignorance, however, is not proof of impossibility. A civilization far more advanced than ours might understand stellar physics in ways we do not. Or it might not need to intervene at all. It could simply observe and wait for natural activity to create an opportunity. At this point, speculation must stop. There is no evidence that 3I Atlas is a weapon. There is no evidence that it influenced the Sun. There is no evidence that any civilization operates according to dark forest logic. These ideas are frameworks for thinking about uncertainty, not conclusions drawn from data. They are unsettling precisely because they are difficult to rule out, not because they are supported by observation. What remains are the facts. An interstellar object with 9 documented anomalies passed through the inner solar system. Its closest approach to the Sun occurred during a period when observation was impossible. A large, magnetically complex sunspot appeared as the object emerged from behind the Sun. The object is now approaching its closest point to Earth. Each of these facts has a natural explanation. Taken together, they form a pattern that draws attention without yielding answers. The scientific response to such a situation is not belief or fear. It is observation. Astronomers continue to track 3I Atlas with increasing precision. They look for deviations from predicted motion. They search for secondary objects. They monitor the Sun. If nothing unusual is detected, the natural explanation grows stronger. If something unexpected appears, models will be revised. For now, the situation remains unresolved. The hidden window at perihelion cannot be reopened. Whatever happened there, if anything happened at all, is beyond direct reach. The object continues on its path. The Sun continues its cycle. The dark forest remains a thought experiment, not a diagnosis. We are left with careful watching and disciplined uncertainty. In science, not knowing is not failure. It is a starting point. There is a thought experiment often used to illustrate the logic behind the dark forest idea, and it does so with unsettling clarity. Imagine standing alone in a vast wilderness at night. You know other people may be out there somewhere, but you cannot see them or hear them. You do not know how many there are, where they are, or what their intentions might be. Now imagine you are holding a flashlight. Turning it on would let you see a small area around you. It would also announce your position to anyone else in the darkness. Anyone watching would know exactly where you are, while you would still know nothing about them. The dark forest logic suggests that the safest choice is to remain unseen. The benefit of illumination is small compared to the risk of exposure, even if most of the unseen figures are harmless. The presence of a single hostile one would be enough to make revealing yourself a fatal mistake. This logic is often used in fiction to explain cosmic silence. In such a universe, civilizations that survive do so by hiding. Those that reveal themselves are eliminated. Whether this reasoning applies to the real universe is deeply contested. Critics argue that it assumes universal hostility, which may not reflect the diversity of intelligent behavior. Cooperation can offer advantages that competition cannot. A civilization capable of interstellar travel might have developed norms, institutions, or ethical systems that reduce the likelihood of preemptive violence. These objections are reasonable and important. The dark forest hypothesis assumes the worst about intelligence and treats fear as the dominant driver of behavior. But the hypothesis does not need to describe all civilizations to matter. It only needs to describe some. A single species willing and able to destroy potential rivals would be enough to shape the behavior of others. In such an environment, even peaceful civilizations might choose silence out of caution. Self-preservation alone would be sufficient if such a civilization existed. Its methods of reconnaissance would likely be subtle. It would not announce itself. It would not broadcast signals. It would gather information quietly and blend into the background of natural phenomena. It would look ordinary. This brings the discussion back to 3I Atlas. There is no claim that it is such a probe. The evidence does not support that conclusion, but if a probe of that kind existed, it might be indistinguishable from a natural object until its work was done. That is the uncomfortable implication of the thought experiment. The dark forest is not a statement about what is happening. It is a reminder of how difficult certainty can be when observation is limited. Thought experiments are not proofs. They are tools for exploring assumptions. They help expand the range of possibilities we consider. Not to replace evidence, but to highlight blind spots. In that expanded space, the convergence unfolding in December 2025 can be viewed from multiple angles without committing to any single interpretation. There is another pattern familiar to anyone who has experienced a major storm. The hours before its arrival often feel unusually calm. Winds die down. Pressure stabilizes. The air feels heavy and still. It can seem as though nothing is happening. Right before everything changes. As of early December 2025, the Sun appears to be in such a phase. The Sunspot complex, designated active region 4294 through 4298, remains active. It has produced multiple M-class flares and several C-class events. On December 1st, a nearby region returned to view with an X1.9 flare, strong enough to cause radio blackouts across parts of the sunlit side of Earth. Yet the most severe outcome has not occurred. There has been no Carrington-class event. This does not mean the danger has passed. A beta-gamma-delta magnetic configuration stores enormous energy. The potential for a major release remains as long as that configuration persists. Sunspots often carry high complexity without producing extreme flares. Energy can dissipate gradually through smaller events. Magnetic fields can untangle slowly instead of catastrophically. But the absence of disaster is not the same as the absence of risk. At the same time, 3I Atlas continues its outward journey from the Sun. Since emerging from solar conjunction in early November, it has been visible to Earth-based observatories during evening twilight. Its coma, the diffuse cloud of gas and dust surrounding the nucleus, has brightened as expected following the intense heating of perihelion. All measurements so far remain consistent with gravitational motion. No propulsion has been detected. No confirmed secondary objects have been observed. The nucleus appears intact, with size estimates ranging from a few hundred meters to several kilometers, depending on assumptions about reflectivity and density. December 19th is approaching. On that date, 3I Atlas will reach its closest point to Earth, at a distance of approximately 269 million kilometers. That is about 1.8 times the distance from Earth to the Sun. In everyday terms, this is not close. The object will not be visible to the naked eye. It will not dominate the sky. But in the context of interstellar visitors, this is an exceptionally close encounter. No confirmed object from beyond our solar system has ever passed nearer to Earth, while we possess the ability to observe it in detail. Oumuamua was discovered only after it had already passed its closest point and was leaving the inner solar system. Borisov never came particularly close to Earth. 3I Atlas presents a rare opportunity. As a result, an extensive observation campaign is underway. The Hubble Space Telescope has been assigned time to image the object. The James Webb Space Telescope is collecting infrared data that may help constrain the composition of the nucleus. Ground-based observatories across the world are tracking its position with extreme precision, refining orbital solutions and searching for even the smallest deviations from prediction. Other spacecraft have also contributed. The European Space Agency's JUICE mission, currently en route to Jupiter, passed within roughly 64 million kilometers of 3I Atlas in early November. Its instruments captured images that are still being analyzed. With data releases expected in early 2026, NASA's Juno spacecraft, orbiting Jupiter, will have an opportunity to observe the object again when it passes near that planet in March 2026. By then, 3I Atlas will be leaving the solar system, but any lingering activity should still be detectable. All of this data gathering is careful and deliberate. Nothing unusual has been confirmed so far. And yet, the convergence continues. The Sunspot complex is slowly rotating toward the western limb of the Sun. In roughly 2 weeks, it will move out of direct view, carried to the far side by solar rotation. While it faces away from Earth, any flares will send their energy into space rather than toward our planet. This creates a temporary window of relative safety. But sunspots can survive multiple rotations. The magnetic structures that generate them persist below the surface even when the visible dark regions fade. If active region 4294 remains coherent during its passage around the far side, it could rotate back into view toward the end of December. That timing would follow shortly after the closest approach of 3I Atlas. Whether this will happen is uncertain. Sunspots decay. Magnetic complexity can collapse quickly. Some large regions disappear after a single rotation. Others persist for months, returning again and again. Space weather forecasters at the National Oceanic and Atmospheric Administration update their assessments daily. Their outlook remains elevated but not extreme. Minor to moderate geomagnetic storm conditions are possible. The probability of a major event remains low. Low, however, does not mean zero. Consider the situation carefully. A sunspot complex roughly 90% the size of the one associated with the Carrington event is present. It carries the most dangerous magnetic classification currently used. It faces Earth now and may face Earth again in a matter of weeks. An interstellar object with 9 documented anomalies will reach its closest approach to our planet during that interval. From December 19th through roughly December 25th, Earth sits at the intersection of 2 rare circumstances. One is certainly natural. The other is almost certainly natural. Together, they form a convergence that feels significant even if it cannot be proven to be meaningful. Nothing has happened yet. The Sun has not produced a Carrington-class flare. 3I Atlas has not deviated from its expected path. All observations to date are consistent with known physical processes. But history shows that the build-up to major events often feels ordinary. Earthquakes strike after long periods of calm. Financial crises erupt after years of apparent stability. Pandemics emerge from normal life. Humans are not good at recognizing precursors before outcomes are clear. Our defenses against space weather are stronger than they were in the 19th century, but they remain limited. Satellites can be placed into safe modes to reduce damage. Grid operators can take some protective actions if given warning. But the warning time for a fast coronal mass ejection can be as little as 15 minutes. That is not enough to protect complex infrastructure fully. Studies estimate that a Carrington-class event today could cause economic damage on the order of trillions of dollars, with power outages lasting months and cascading failures across communications, transportation, finance, and healthcare. These estimates are not speculative. They come from engineers and analysts who have examined the systems in detail. Whether such an event occurs this month, this year, or decades from now is unknown. What is clear is that the risk exists. And now, we wait. 3I Atlas continues its approach. The Sun continues its rotation. Forecasters monitor the data. Observatories collect measurements. Daily life goes on, supported by systems that are more fragile than they appear. The quiet before is not peace. It is suspense. Something may happen. A large solar flare. An unexpected anomaly in the trajectory of the interstellar visitor. A discovery that forces a revision of current understanding. Or nothing may happen at all. The sunspot may decay. The object may pass without incident. December may fade into January. And the convergence may be remembered as coincidence. We cannot know in advance which outcome awaits us. We can only observe, prepare where possible, and acknowledge uncertainty. Storms eventually come. Calm periods always end. December 19th approaches. The ancient traveler draws near. The sun continues to release energy into space. And for now, we remain in the quiet, waiting to see what follows. The attention now focused on 3I Atlas represents the most comprehensive observation campaign ever directed at an interstellar object. Never before has a visitor from beyond our solar system been examined by so many instruments, across so many wavelengths, operated by so many agencies at the same time. For a brief window in late 2025, this third confirmed interstellar arrival has become the most closely watched small body in the sky. The data being collected will take years to fully analyze, but the opportunity itself is fleeting. Once the object recedes, it will be gone forever. This campaign is not driven by speculation. It is driven by rarity. Interstellar objects offer direct physical samples of material formed around other stars. They carry information about environments we cannot otherwise reach. 3I Atlas is passing close enough, and at a time when our observational capabilities are mature enough, that scientists have mobilized everything available to learn as much as possible while they can. One of the central tools in this effort is the Hubble Space Telescope. Launched in 1990 and still operating more than 3 decades later, Hubble remains unmatched in its ability to deliver sharp images free from atmospheric distortion. From Earth's surface, turbulence in the atmosphere blurs fine detail. Hubble, orbiting above that atmosphere, sees with clarity that ground-based telescopes struggle to achieve. For 3I Atlas, Hubble's role is primarily structural. It can resolve the shape and distribution of the coma, the cloud of gas and dust surrounding the nucleus. It can track how brightness changes across that coma over time, which may reveal the rotation of an irregularly shaped nucleus or the presence of localized jets venting material from the surface. Hubble has already observed the object during its inbound journey, and additional imaging is scheduled around the December closest approach, where Hubble excels at visible light. The James Webb Space Telescope extends our reach into the infrared. Launched in 2021, Webb is designed to detect heat and chemistry rather than shape alone. Infrared observations are especially powerful for comet-like objects. Different volatile substances release gas at different temperatures, and each molecule absorbs and emits infrared light at specific wavelengths. By spreading that light into a spectrum, Webb can identify which molecules dominate the coma. For 3I Atlas, Webb has already confirmed something unusual. The coma is dominated by carbon dioxide rather than water vapor. In comets formed in our own solar system, water ice typically drives activity once the object nears the sun. Carbon dioxide sublimates at lower temperatures than water, which suggests that for an object that spent billions of years in the extreme cold of interstellar space, carbon dioxide may become active first. This result does not imply anything artificial, but it does point to a formation and thermal history different from that of most familiar comets. Webb's infrared data also helps constrain the physical properties of the nucleus itself. By measuring how much heat the surface absorbs and how much it radiates away, astronomers can estimate the albedo, or reflectivity, of the surface. Combined with brightness measurements, this helps narrow down size estimates and surface composition models. These are slow, careful inferences, but they matter. They tell us whether 3I Atlas is more like a compact, rocky body or a porous, icy one. Ground-based observatories play a complementary role. Facilities such as the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the Gemini telescopes in both hemispheres provide high-resolution spectroscopy across visible and near-infrared wavelengths. Spectroscopy allows scientists to detect specific atoms and molecules in the coma with high precision. One of the most closely watched measurements is the ratio of nickel to iron in the gas surrounding the nucleus. As noted earlier, this ratio appears unusually high compared to typical comets. Continued observations will help determine whether this reflects the bulk composition of the object or a surface effect caused by long exposure to interstellar radiation. Either outcome carries implications for how and where the object formed. Beyond traditional telescopes, several specialized space missions are contributing context that Earth-based instruments cannot provide. The Parker Solar Probe, which travels closer to the Sun than any spacecraft before it, observed the region around 3I Atlas during its perihelion passage from a unique vantage point. Parker's primary mission is to study the solar corona and solar wind, but its instruments can also register objects moving through that environment. Any data collected during the perihelion window is particularly valuable, because that was the period when Earth-based observation was impossible. The Solar and Heliospheric Observatory, known as SOHO, has monitored the Sun continuously from the first Lagrange point since 1995. Its coronagraphs block out the bright disk of the Sun to reveal the faint surrounding corona. These instruments captured images of 3I Atlas as it passed behind the Sun. The images show the object brightening as it approached perihelion, consistent with increasing activity driven by solar heating. This behavior aligns with expectations for a cometary body. Another mission, PUNCH, launched in 2024, is designed to study how the solar corona connects to the heliosphere. Its instruments detected 3I Atlas in late October as the object neared perihelion. That data is still under analysis, but it adds another perspective on how the object interacted with the solar environment during the hidden window. The European Space Agency's JUICE mission provides one of the most unusual opportunities. Launched to study Jupiter's icy moons, JUICE is currently in its long cruise phase. By chance, its trajectory brought it within roughly 64 million kilometers of 3I Atlas on November 4th, just days after perihelion. Although JUICE was not designed for comet science, several of its instruments can be repurposed. Its visible light camera can capture detailed images. Its infrared spectrometer can analyze thermal emission. Its sub-millimeter wave instrument can detect certain molecules in the coma, These observations represent the closest post-perihelion encounter with the object so far. The analysis is ongoing, with results expected in early 2026. They may reveal surface changes caused by extreme heating that cannot be resolved from Earth. Looking further ahead, NASA's Juno spacecraft at Jupiter will have an opportunity to observe 3I Atlas again in March 2026 as the object passes near that planet. By then, it will be well on its way out of the solar system, and its activity will be fading. Even so, residual outgassing and precise trajectory measurements will add valuable constraints. With all these instruments engaged, it is worth asking what scientists are actually looking for. At the most basic level, they are building a complete physical profile. Size, shape, rotation rate, composition, and activity patterns all matter. Together, these properties tell a story about where the object formed and what it experienced during its long journey between stars. But beyond characterization, researchers are also watching for deviations. Comets often experience small, non-gravitational accelerations caused by jets of gas acting like tiny thrusters. These effects can be modeled if the outgassing is understood. If 3I Atlas shows acceleration that cannot be explained by observed activity, that would demand closer scrutiny. This is not without precedent. Oumuamua, the first confirmed interstellar object, exhibited a small but measurable non-gravitational acceleration near perihelion. The leading explanation involved outgassing of volatiles that were difficult to detect. But the issue remains unresolved. 3I Atlas provides a chance to see whether such behavior is common among interstellar visitors or whether Oumuamua was exceptional. Another focus is fragmentation. If material was released during the perihelion passage, whether through natural processes such as thermal stress or tidal forces, it should separate from the main nucleus over time. Radiation pressure and gravity would cause fragments to drift apart along predictable paths. By December, any significant separation should be detectable. So far, no confirmed fragments or companion objects have been observed. The nucleus appears intact. But surveys continue, and any new detections would be reported quickly. Chemistry remains central. Beyond nickel and iron, scientists are scanning spectra for any unexpected absorption or emission features. Even the absence of expected lines can be informative. This is exploratory science in its purest form. Models predict what a natural interstellar comet should look like. Observations are compared against those models. Where they match, confidence grows. Where they diverge, new questions emerge. All of this work faces practical limits. 3I Atlas is moving fast, well over 100,000 miles per hour relative to the Sun. From night to night, it shifts noticeably against the background stars. Telescopes must constantly update their pointing. Exposure times must balance motion blur against signal strength. The coma complicates everything. Unlike asteroids, comets surround themselves with material that scatters and absorbs light, obscuring the nucleus. Extracting nucleus properties requires careful modeling and subtraction of the coma's contribution, which introduces uncertainty. Distance is another constraint. Even at closest approach, nearly 270 million kilometers away, angular resolution is limited. Features that would be obvious on a nearby object collapse into points of light. Yet the instruments and techniques in use represent decades of refinement in cometary science. Different measurement techniques contribute different pieces. Photometry tracks brightness changes over time. Periodic variations can reveal rotation rates and constrain shape. For 3I Atlas, brightness fluctuations on the scale of hours have been detected, consistent with a slowly rotating, Irregular nucleus. Astrometry measures position with extreme precision, allowing scientists to detect even tiny deviations from predicted motion. Polarimetry examines how light is polarized by scattering, providing insight into dust particle size and structure. The extreme negative polarization observed in 3I Atlas is one of its most distinctive anomalies. Each technique alone offers limited insight. Together, they build a portrait that will be studied long after the object has gone. The timeline, however, is unforgiving. 3I Atlas will be close and bright enough for detailed study for only a short time. After that, it will fade, slipping beyond the reach of even the most powerful telescopes, carrying its secrets back into interstellar space. This is a single chance. The international astronomy community understands that. Observation time has been allocated. Resources have been committed. Data is flowing now. If 3I Atlas is a natural comet, these observations will deepen our understanding of how planetary systems form around other stars and what materials populate the galaxy. If it is something more unusual, the evidence will have to come from these measurements. Whatever the answer, it will be written in the data streams already being recorded. The telescopes are watching. The instruments are measuring. The analysis pipelines are filling. Somewhere in that vast collection of numbers and spectra, the nature of this ancient traveler is encoded, waiting to be read. In the weeks following the discovery of 3I Atlas, something notable unfolded online. The usual background noise of speculation did not simply increase. It surged. Claims multiplied. Theories branched. And fragments of information were copied, reshaped, and reposted at speed. Within that growing torrent, one particular story rose above the rest and spread with unusual intensity. The story claimed that 3I Atlas was emitting signals, not random noise, but deliberate transmissions. According to these claims, the object was producing regular pulses at intervals of 147 seconds. The pulses were said to contain numerical structure, specifically the Fibonacci sequence, a series in which each number is the sum of the two that come before it. The alleged transmission frequency was 1420 MHz, the so-called hydrogen line. In astronomy, this frequency has long been suggested as a logical choice for interstellar communication because it corresponds to the natural emission of neutral hydrogen, the most abundant element in the universe. The narrative spread rapidly across social media platforms. It appeared on tabloid-style websites. It was attributed to unnamed scientists, to leaked documents, to intercepted data streams. In some versions, the pulses had already been decoded. Phrases appeared again and again. Observe. Prepare. Understand. The gate awaits. The language was dramatic. The implications were clear. And none of it was confirmed. It is important to be explicit about the status of these claims. There are no peer-reviewed scientific papers documenting the detection of artificial signals from 3I Atlas. There have been no official announcements from major observatories, space agencies, or radio astronomy facilities confirming electromagnetic emissions of non-natural origin. The stories circulating online do not cite sources that can be independently verified. This does not prove the claims are false. It means they are unsubstantiated. Some versions of the story invoke the physicist Michio Kaku, suggesting that he had described pulses that should not exist in nature. However, no scientific publication by Kaku supports this claim. The quotations attributed to him appear to originate from short-form online video content rather than academic work. This distinction matters. Viral commentary is not the same as scientific reporting. Avi Loeb has, in fact, discussed what he refers to as the heartbeat of 3-eye atlas. This phrase describes observed brightness variations that occur at regular intervals. This is a real observation. Cometary nuclei often rotate, and as they do, different surface regions with different reflectivity rotate into view. This produces periodic changes in brightness that can be measured. The rotation period provides useful physical information about the object. But a rotating comet is not an artificial transmitter. Periodic brightness variation is not the same as encoded communication. The reasons these claims spread so widely are worth examining. Humans are pattern-seeking by nature. We evolved to detect structure in noisy environments, faces in clouds, meaning in coincidence. At the same time, modern culture has spent decades imagining contact with extraterrestrial intelligence through science fiction, through search programs like SETI, through debates about the Fermi paradox. The idea of visitors from beyond our solar system is deeply embedded in the collective imagination. When an unusual object arrives from interstellar space, the conceptual framework is already waiting. When that object also displays anomalies, when its trajectory seems statistically unusual and its composition does not fit neatly into familiar categories, the leap to artificial origin becomes tempting for some observers. Online analysis suggests that roughly 40% of social media discussion about 3-eye atlas invokes extraterrestrial intelligence in some form. This is not a fringe belief confined to a few voices. It is a substantial portion of the public conversation. Desire, however, is not evidence. The longing for contact does not change the standards of proof. This raises a key question. What would a genuine artificial signal actually look like? This question has shaped the field of the search for extraterrestrial intelligence for decades. The central challenge is separating intentional communication from natural phenomena and from human-made interference. Nature is capable of remarkable regularity. Pulsars, rapidly rotating neutron stars, emit radio pulses with precision rivaling atomic clocks. When pulsars were first detected in 1967, their regular signals briefly led researchers to consider artificial origin. They were jokingly labeled LGM, for little green men. Before their true nature was understood, artificial communication would presumably carry information. Random pulses are not messages. To qualify as a signal in the meaningful sense, there must be structure that encodes content. Mathematics is often proposed as a universal language. Sequences such as prime numbers or the Fibonacci series are frequently suggested as unmistakable markers of intelligence. But detecting information requires ruling out every plausible natural and instrumental explanation first. This is extremely difficult. Instruments produce noise. Electronics generate spurious signals. Software contains bugs. The history of SETI is filled with false alarms that initially seemed promising and later proved mundane. The most famous example remains the WOW signal. On August 15, 1977, astronomer Jerry Amen was reviewing printouts from the Big Ear radio telescope at Ohio State University when he noticed a strong, narrowband signal at 1420 MHz. The signal lasted 72 seconds and then vanished. Its intensity stood well above background noise. Amen circled the data and wrote the word "wow" in the margin. Follow-up observations found nothing. Despite decades of searching, the signal has never been detected again. Explanations have ranged from natural radio sources to reflected terrestrial transmissions to unusual hydrogen emissions associated with a passing comet. None has been definitively confirmed. The WOW signal remains unexplained. And its legacy illustrates how difficult it is to establish artificial origin. One detection, no matter how striking, is not enough. Repeatability is essential. Independent verification is required. Alternative explanations must be exhausted. For 3I Atlas, the evidentiary bar is even higher. The object is moving rapidly. Its orientation and geometry change from night to night. A signal detected at one moment might not be detectable later for purely geometric reasons. The observation window is limited. Within a few months, the object will be too distant for detailed study. The online claims do not meet scientific standards. They are not supported by documented observations. They have not been verified by independent teams using different instruments. They rely heavily on screenshots, anonymous posts, and viral videos. But they do reflect something genuine about human psychology. We want there to be signals. We want the interstellar visitor to mean something. We want confirmation that intelligence exists beyond Earth. This desire is understandable. The probability arguments behind the Fermi paradox suggest that intelligent life should be common. The galaxy contains hundreds of billions of stars, many host planets. The timescales are vast. Our continued failure to detect clear evidence creates tension. Surely someone should be out there. Surely we should have heard something by now. So when an interstellar object arrives, carrying anomalies that mainstream science has not fully resolved, the temptation to interpret it as contact becomes powerful. The viral claims are not evidence of signals. They are evidence of hope. There is a useful framework for evaluating future claims. First, consider the source. Peer-reviewed research is more reliable than anonymous posts. Scientists speaking on the record are more reliable than quotes extracted from viral content. Official statements from observatories and space agencies carry more weight than tabloid speculation. Second, consider verification. Has the observation been independently confirmed using different instruments? Single detections are fragile. Multiple confirmations are not. Third, consider alternatives. Have natural explanations been rigorously examined? Has interference been ruled out? Finally, consider information content. Regularity alone is not enough. Communication implies structure that can be decoded. By these standards, the current claims about signals from 3I Atlas do not hold up. The documented observations are consistent with natural cometary behavior. The extraordinary evidence required for extraordinary claims has not been presented. This does not prove the claims are false. It means they are unproven. 3I Atlas will continue to be observed. If genuine signals are detected, they will be documented, verified, and announced through established scientific channels. Until then, the so-called Fibonacci whisper remains just that, a whisper in noise, a hope reshaped into rumor, a projection of our desire for contact onto ambiguous data. The silence of the cosmos persists, and in that silence, we continue to imagine what we wish to hear. The history of SETI is a history of patience and disappointment. For more than 60 years, radio telescopes have scanned the sky. Billions of frequencies have been sampled. Millions of stars have been observed. The result has been silence, interrupted only by anomalies that could not be confirmed. Projects such as Breakthrough Listen have expanded the search dramatically. Using some of the most powerful radio telescopes on Earth, the data continues to be analyzed. No confirmed artificial signals have been announced. The absence of evidence is not evidence of absence. Our searches cover only a fraction of possible frequencies. Our assumptions about how others might communicate may be wrong. A civilization that wished to remain hidden could do so easily. This is why claims about 3I Atlas draw attention. A physical interstellar object offers a different kind of possibility. Not a signal racing at the speed of light, but a tangible visitor moving slowly enough to be studied. The claims circulating online reflect a longing to find meaning in uncertainty. That impulse is human, but science demands restraint. Hope must wait for evidence. The burden of proof remains high. And still, the questions remain. 9 anomalies, a hidden window, a sunspot of historic scale, a convergence in December. The data does not support claims of artificial signals, but the data also does not close every door. 3I Atlas will leave our solar system. It will not return. Whatever answers it carries may leave with it. Science does not always provide closure. Sometimes it leaves us with probabilities rather than certainties, with patterns rather than conclusions. The universe is not obligated to resolve our questions. The convergence. We now find ourselves at the crossing point of 2 very different paths. One began its journey roughly 8,000 years ago, moving through interstellar space at speeds far beyond anything human technology has achieved. The other emerged from the turbulent magnetic interior of our own star, a disturbance on a familiar surface that appeared just as the visitor drew near. 3I Atlas will reach its closest approach to Earth on December 19th. The Sunspot complex, designated AR4294, may rotate back into an Earth-facing position around the Christmas period. This is not a collision. It is a coincidence of timing. But it is a coincidence that invites questions we cannot answer and cannot fully ignore. There are things we can state with confidence. 3I Atlas is an interstellar object, only the 3rd ever confirmed, following a hyperbolic path that will carry it through our solar system and back into interstellar space. Its trajectory brought it within 5 degrees of the ecliptic plane, close to multiple planets, and to its closest approach to the Sun during a 2-week period when Earth-based observation was impossible. The object displays 9 documented anomalies: unusual trajectory alignment, unusual timing, unusual composition, unusual inferred mass, unusual polarization, unusual survival through perihelion, unusual color behavior, unusual activity patterns, and the clustering of these features around a single visitor rather than being spread across many objects. We also know that the Sunspot complex, labeled AR4294 through AR4298, is among the largest and most magnetically complex active regions of solar cycle 25. It appeared as the interstellar object emerged from behind the Sun. Its magnetic classification indicates the capacity to produce X-class solar flares. In principle, events approaching Carrington-class intensity. We know from historical and modern analysis that a Carrington-class geomagnetic storm today would have severe consequences. Power grids could fail. Satellites could be disabled. Communications disrupted. And an infrastructure built on electromagnetic stability would be pushed beyond its limits. What we do not know is whether these 2 phenomena are related. The prevailing scientific consensus is that they are not. The Sun produces large sunspots during periods of peak activity. Interstellar objects follow trajectories governed by gravity and initial conditions, not by solar behavior. From this perspective, the timing is coincidence and the convergence has no deeper meaning. This explanation may well be correct. It is probably correct. In science, the simplest natural explanation should remain the default unless evidence clearly demands otherwise. Yet the evidence is incomplete. The hidden window at perihelion means we lack direct observation during the most energetic phase of the object's passage. The Oberth effect tells us that perihelion is the moment when even small actions would have the greatest impact on trajectory. Broader ideas, such as the dark forest hypothesis, raise the possibility that advanced civilizations might exploit natural-appearing phenomena if they existed. At this point, we are in the realm of speculation. Speculation is not evidence, but it is not meaningless. It is the exploration of what could be true before we know what is true. If 3I Atlas is entirely natural, then December 2025 represents an extraordinary coincidence. An interstellar visitor and a historically large sunspot align in time by chance alone. Such alignments can occur in a large, indifferent universe. They carry no message and no intent. They simply happen. If the object is something else, the same convergence takes on a different interpretation. A probe arriving during solar maximum, a trajectory that coincides with potential solar disruption, a test of our ability to observe, interpret, and respond. There is no evidence that supports this interpretation over the natural one, but geometry and timing prevent us from ruling it out with certainty. What, then, should we take from this moment? Perhaps humility. Humanity has been spacefaring for less than 70 years. We have known about interstellar objects for less than a decade. Our understanding of solar physics, cometary behavior, and the broader possibilities for life in the universe remains incomplete. Much of what we know is provisional. Perhaps vigilance. The sunspot remains active. Space weather is a real and ongoing risk independent of any interstellar visitor. Our technological systems are vulnerable, and our preparations remain limited. Even if December passes quietly, future solar cycles will not. The underlying risk does not disappear. Perhaps wonder. We live in a universe where material from other star systems can pass through our own. These objects carry information about environments we will never visit directly, about chemistries and histories older than our Sun. 3I Atlas likely formed between 7 and 11 billion years ago, in a system that may no longer exist. It is a physical remnant of deep cosmic time, perhaps perspective. A century ago, this object would have passed unnoticed. 1,000 years ago, its presence would have been entirely invisible. We are the first generation with the ability to detect, track, and study such visitors in detail. That alone is significant. How this period will be remembered remains uncertain. It may become a historical footnote, a case study in coincidence during solar maximum, or it may acquire greater meaning as new data is analyzed. We cannot know from within the moment itself. We can only observe carefully, record faithfully, and interpret cautiously. 3I Atlas will pass closest to Earth in days. The sunspot will rotate out of view and may return. Data will continue to arrive from observatories around the world, and analysis will continue for years. Whatever happens next, it will be documented. Occasionally, the universe sends us something tangible rather than a signal, not a message encoded in radio waves, but an object moving through space, visible for a short time before returning to darkness. Such visitors do not answer our questions. They deepen them. 3I Atlas will leave our solar system. It will travel on, passing near other stars long after our own moment has ended. Whatever secrets it carries will go with it. We cannot follow. We can only watch until it fades beyond detection. In the brief window during which it is visible, we have gathered more information than ever before. We will remember its discovery, its approach, the hidden window at perihelion, the appearance of the sunspot, and the convergence in December. We will continue to debate whether we understood what we were seeing. Interstellar objects appear to be more common than once believed. The detections of Oumuamua in 2017, Borisov in 2019, and now 3I Atlas suggest a population of wandering debris between the stars. This fits naturally with models of planetary formation and ejection. Most such objects are small and dark, We detect only the rare few that are large or active enough to stand out. Even so, questions remain. Some anomalies resist simple explanation. Perhaps they reflect unfamiliar natural processes. Perhaps they reveal gaps in our models. Or perhaps we are imposing patterns where none exist. The universe offers no assurances. It does not explain itself. It unfolds according to physical laws that operate without regard to human expectation. And still, we observe. We measure. We ask questions. The interstellar visitor continues its journey. The sun continues its cycle. Earth continues to turn beneath both, fragile and resilient at once. Whatever the outcome of this convergence, the act of watching itself matters. It is how knowledge advances. It is how uncertainty is reduced, even when it cannot be eliminated. The darkness between stars is not empty. Objects pass through it, carrying histories far older than our own. For a brief moment, one of them passed through our view. We looked, we recorded, and we will continue to learn from what we saw, long after it is gone.